what everyone else is doing, but I'm starting. All right, so last class, when we did our separation of variables,
I just want to wave hi to
and
myself.
derived the equations for r, theta, and phi. We ended up with an equation for the theta portion of the differential equation. So this is going to be the solution for the theta portion. That included an integer that came from matching up the theta and the r portions of in the separation of variables. And we did this because the solution ended up giving us Legendre polynomials, right? And then we had the phi portion. And what we did initially, actually what we did last class, was to assume that the solution in phi in azimuth was independent of angle, right? So it was just constant. So we set, in this equation here, m equal to 0. And setting m equal to 0 led to solutions to this equation, which were Legendre polynomials, right? And the Legendre polynomials are in x, but x is equal to cosine theta. So we're actually got a more complex behavior than that. And I talked about the basic forms, or actually the lowest orders of these Legendre polynomials that were solutions to that equation up there. Right? Now, if m is not equal to 0, then we've got to solve this whole equation. Right? If we had, without m, this is the Legendre, well actually they're both Legendre equations, but the solutions are Legendre polynomials, which I showed you, right? With m, now I've got an m and an l here, and it will turn out that there are going to be constraints placed upon what m is allowed to be, right? I can't just arbitrarily choose them, because otherwise I'll end up with I'll end up with derivatives that just turn out to be 0, right? So m is going to be limited in what quantities it can actually be. And the relationship between the Legendre polynomials and the associated Legendre polynomials can be found simply but the relationship can be tested easily, right? They cannot be found simply, but it can be tested in that the PLMs, when m is not equal to 0, look like this. 1 over 1 minus x squared, absolute value of m over 2. The absolute value of m so we're going to take the nth derivative of the Legendre polynomial. Okay? So this is what the PLMs actually look like. And if we know the Legendre polynomials, which we have a generating function for the Legendre polynomials, then we can generate our associated Legendre polynomials. And associated Legendre polynomials have two indices, L and M. And we have the constraint that M can only take values between minus L, and it has to have integer values. And L are integers. Most of the time, we're only going to need to know a few of these functions, and you can actually look them up in your handy shelves if you don't want to actually go through and use generating functions in order to find them. So the associated Legendre polynomial for L equals 0 and M equals 0 is 1. P10, again, we already found that one, is x, because we're not taking any derivatives then. But we can have L equals 1, M equal to plus or minus 1. And that's 1 minus x squared, square root. P20 should just be the Legendre polynomial. Start taking derivatives. And P2 plus or minus 2. And then maybe I'll leave P3s to you. Figure out 3x minus 5x cubed. And then you can just take derivatives in order to find out what the rest of the values are. Yes?
So for M and L, is it less than or equal to, or just less than?
Oh, thank you. Or equal to, as my examples seem to show.
I thought so.
Yeah. Okay. And don't forget then that we had solutions in phi, that the overall spherical solution looks like an e to the I m phi times p l m times r to the, let me just, for example, take one of the solutions, r to the l, and there's going to be some normalization for that. So that's one possible solution, all right? I can have minus m, I can have minus l. When I include them all, I have to do the entire sum of the complete set of functions and then figure out what behavior matches the boundary conditions, okay? So the full solution looks something like that, all right? And we'd actually like to normalize the full solution so that we have a set of functions that we can we can use the orthogonality and orthonormal relations on, so that then we can do expansions, series expansions, to figure out what the potential is in a certain region of space. So, we'll actually worry just then about the associated Legendre polynomials and the dependence on the azimuthal angle, right? And those can be written, or are written, in normalized form. They are called in normalized form.
That's good to me.
Spherical harmonics. And spherical harmonics, which are the normalized form that include the I to the m phi, right, are usually written as a capital Y, L, M. They are functions of theta and phi. And then normalized, this is messy, but we only have to worry about it once. 2L plus 1 over 4 pi L minus M factorial over L plus M factorial P L M of cosine theta times e to the I m phi. sorry, ran out of space. But I've got the phi dependence, the theta dependence, and a factor that normalizes the two so that the integral over theta and phi of y L m y L m prime, let's say, d theta d phi is, oops, L prime m prime. D theta d phi is delta L L prime delta m m prime. It's 1. Okay? This is, again, we can realize that that could be really useful if we're given the potential on a particular boundary. Then we plug in that particular boundary condition and then multiply both sides by y L prime m prime, for example. Do the integrals, and as those YLMs, the spherical harmonics, form a complete set of functions on theta and phi, so we can describe any function that we want on theta and phi. Okay? I have not yet. Well, actually, what I've just written has been posted in Lecture 5, because this was the tail end of Lecture 5. What I'm going to do is proceed with some more ideas now, and then I'll come back, if there's time at the end, to actually do some specific examples of problems on, that use spherical harmonics for the solutions. And actually, just general problems with different, or spherical and cylindrical problems with different boundary conditions, so that you can see how we go through those. But before I do that, or before I do anything else, I'll just comment that very frequently you can inspect the boundary conditions that you've got. And first of all, you can inspect and eliminate, because you know that potential's got to fall off and go to 0 at infinity and so on, right? But in addition, very frequently the boundary condition that you've been given is one that doesn't actually require the doing of the integral. You can just look and say, oh, that's the cosine 2 pi form. There's cosine 2 pi over there. Those are the same. Done. Right? Those are the only. That's the only one that's not 0 that you have. You just look to see when you've got L prime and M prime not 0, or rather the same as L and M, for example. So if you know the form of the spherical harmonics, then you can look at your boundary conditions and see if they look like your spherical harmonics. On page 24 of the last notes, I'll just pull this up. Too close.
Actually, that's perfect.
Okay. You can't see this, though. But I have the first 4 spherical harmonics written out with all 4 pi's and everything. Right. So that's in the notes. But if you just look under spherical harmonics in Schaum's, you'll find a table of them. But I guess I should comment, I think that Ohanian and Griffiths don't do very much with spherical harmonics. I think that this is the goal. Finally, we get to being able to explain everything in the full space over both sets of angles. But for some reason, they just say they exist and leave it at that. Writing them out is somewhat important. Okay. So now I'm going to do a little bit of a review, because many of you, and that includes me when I was a student, can listen to me talk about expansions and series solutions and not see how easy it is. So let me just talk about the general idea yet again. using slightly different words and hope that the epiphany hits this time around. Epiphany's actually January, right? Who knows?
Oh.
When Epiphany comes.
January 6th.
January 6th, yeah. My Spanish mother used to say that that was when the devil came to take down the Christmas tree. So that's how I remember January 6th. Please erase that from
Nah. We just take it down, chop it up, and use it for firewood at my house.
Christmas trees make bad firewood.
It's called a Yule log.
Okay, so what I've been talking about for the past couple of classes are the applications of orthogonal sets of functions that are solutions to a specific type of equation. And it's just like it gives you a little bit of bragging right to know the name of the specific type of equation. So I'll write it down again. Sturm Liu. And it distinguishes people from New York City from everyone else because people from New York City say Storm Louisville. If you do that, then they know you're from the Bronx.
I should ask my mom.
Or at least that was true when I was at Brooklyn Poly.
I should definitely ask my mom.
Yeah, anyway.
I hope you realize this is being caught on camera. All of your
And
comments.
all differential equations
My mom's
of the
from
Sturm-Liouville type result in solutions that form orthogonal and complete sets of functions. Right? So we had an equation that looked like this. E squared x dx squared plus k squared x is equal to 0. And the solutions to that look like sine functions and cosine functions. X is the sum over all possible ends. And then we have to we will satisfy boundary conditions, find out what the a sub ends are. And by x. There we go. This is the periodic boundary conditions. So we have a differential equation for which the solution is found on a certain range. And in this case, the range goes from plus L to minus L. And the sine and the cosine functions form an orthogonal set, and when properly normalized, give us an orthonormal.
You're also missing a parentheses.
There you go. Thank you.
I think that he's missing.
Right. And
Technically.
so what we do is we look at the boundary conditions of the particular problem that we're given, and based upon the boundary conditions, we figure out what the a sub ends and b sub ends have to be in order for the function x to have a certain functional form at a particular, right, which satisfies the boundary condition. In cylindrical coordinates, let's see, I did write it down. Here's another one. R squared, b squared, r squared plus r. Oops, there's more. That one is also Sturm-Liouville. And the solutions to this are Bessel functions. Which look like sine and cosine functions that decay as 1 over a power of r. Right? And Bessel functions, with the appropriate weighting, are also form an orthogonal and orthonormal set of functions, complete set of functions, over the interval from 0 to 1, but we can always scale. So the Bessel functions would be J R, let's say, but normally we'll scale R in order to set the interval to go from 0 to 1, because these are radial solutions. So, yeah, I said these are radial solutions to Laplace's equation in cylindrical coordinates. Actually,
There's one over
polar
R.
coordinates. What?
But keep on.
All right. And then we had the Legendre functions
Camera.
for spherical coordinates with azimuthal constancy, just symmetry, constancy, right? Which we just talked about. And the solutions to that differential equation obey
No, I talk to myself. This is true.
P sub L prime, X is delta L prime times. And over here, actually, I might as well write down the Bessel function relationship. Integral 0 to 1 of R J the
Possibly.
I'll make it P of R J sub, oh, it's, never mind.
Bessel functions are J's.
Bessel functions, two Bessel functions. Bessel functions are called J. And this will be I'll use L prime. Yes, okay, actually, you're right. Actually, the ends, I think, are called Neumann functions. But it turns out that the ends are non-physical. So we have only Bessel functions as the solutions. Yes.
Shouldn't those be J's too instead of P's?
No, these are, oh, I'm sorry. I should have been more clear here. So over here where Bessel functions are the solutions to that equation. I will finish this in a minute. I'll come back to this. I went back there. I will come back to this. Our J sub L of alpha R L prime of beta R is equal to delta L prime delta alpha beta, so the coefficients have to be the same, 1/2 J squared of L plus 1 alpha. You choose alpha or beta, okay? A couple of things to note, this is dr, is that there is a weighting function here, where we are multiplying these functions by this r in order to make the orthogonality work, right? That's a property of Sturm-Liouville equations, that the solutions are orthonormal when weighted in a certain way. And luckily enough for us, for this solution to, this was cylindrical, radial equation, all right? For this solution, when we actually look at what the formula of solutions has to be, it turns out that we have to weight by r in order to, that the solutions include that. So now, for spherical Laplace's equation, or Laplace's equation in spherical coordinates with azimuthal constancy. Right? Then the equation looks like this. I've written this down before, but I'll write it down again. 1 minus x squared d squared e d squared minus writing it out 2x p dx plus L times L plus 1 p equals 0. Okay? And the Legendre solutions to that are, have this orthogonality. I can integrate over x. And then I just wrote down, so I'm not going to write down again, the equation and the solutions for full spherical Laplacian, where you don't have to have absolute constancy, right? Where you've got an e to the I and phi. So, and there are others, but these are the ones that you're going to need in this course: quantum physics, quantum mechanics, and that's probably, I'm trying to think whether you use them in theoretical mechanics or not. But you certainly use these problems in electromagnetic problems and quantum mechanics.
I don't think we use them in TMAC.
Okay.
I don't remember.
Although, by the way, I mean, actually, if you come back here, this is an oscillator. Right? So, you know, you can talk about waves on a string, for example, and we can talk about, well, that's electromagnetics, diffraction of light, and I think waves on a drumhead. And
So you could do sound
heat
waves
flow.
with
Yes.
the spherical.
Yes. Okay. So the process, though, is first look at your problem and decide what the simplest symmetry to solve the problem in is. Okay. If the potential is defined on a spherical surface, that's what you're going to use. If it's defined in rectangular coordinates, that's what you're going to use. So first decide which set of functions you're going to use. Each of them will solve for the full Laplacian, the solutions to Laplace's equation in some space. It's just a question of whether the answer is going to converge quickly or whether it's going to be really messy, right? So you choose your geometry, the geometry of the solution, in order to match your boundary conditions as best you can. Once you've done that, then you express your solution on some boundary in terms of a sum of sines or vessels or spherical harmonics. Actually, not vessels, because actually the cylindrical radial problem, the angular problem, is actually just a Fourier series. Again, the solutions in angular sines and cosines, and with integer terms. Okay. So when you're actually trying, if you have your potential defined on a cylindrical surface, then most frequently you're just going to be using a Fourier series to express that. And then the cylindrical functions come along for the ride. Okay? So, but all of these form complete sets of functions. All right. Okay, next will be multipole expansions, and I'm going to take a few minutes break before we do that. So.